So in section 2.4, we're going to learn a few more rules for derivatives, probably the last rules that we'll learn for the semester. But I want to quickly, maybe not so quickly because I can't do anything quickly, but teach a shortcut for the chain rule. I didn't want to introduce the shortcut for the chain rule when I was doing section 2.3 because a lot of times students they learn the shortcut wrong. So I'm going to just do, well, maybe 4 problems that we can use the chain rule for. Remember, the chain rule is something that we use when there's an exponent that we don't care to get rid of. So this would be a classic chain rule problem, and we could make the f of x, set the parentheses equal to g of x, make f of x equals 3x to the 6, but that's the slow way to do it. The shortcut for the chain rule is when you have a parentheses with an exponent, you can find the derivative by kind of using the power rule, as long as you multiply by the contents, the derivative of the contents of the parentheses. So I'm going to do the chain rule like the power rule, meaning I'm going to multiply the exponent by the coefficient. I'm going to lower the exponent by 1. And notice I left myself some room. So that would be like using the power rule, multiplying the exponent by the coefficient, lowering the exponent by 1. But that's not enough when there's a parentheses that has some junk in it. And you finish up the problem by multiplying by the derivative of the inside of the parentheses. So right here, I'm going to multiply by the derivative of the inside of the parentheses. The derivative of x squared, I bring the 2 out front, I lower the exponent by 1, I get 2x to the first power. The derivative of 5x is just 5. And that's the entire derivative, except I'm going to multiply the 6 and the 3. So I'll do 3 more of these shortcuts, just so you can get it down. So I'm going to make up a new function, and I'm going to do the shortcut derivative. So I'm going to do g of x equals 3x plus 9 to the 4th power. Again, it has a parentheses with an exponent, so the chain rule is the proper way to take the derivative. There's a shortcut for the chain rule. I'm going to take the 4, multiply it by the number that's in front of the parentheses. There's an implied 1 there, so I'm multiplying 4 by 1. I'm going to write g prime of x because I'm doing the derivative. I'm going to bring the 4 down. I'm going to leave myself some room, and then I'm going to write the inside of the parentheses unchanged, lower the exponent by 1. So that's kind of using the power rule. Multiply the exponent by the coefficient, lower the exponent by 1. I leave myself some room. I put a times sign, and after that times sign I put the derivative of the contents of the parentheses. Last time I needed a parentheses because there were 2 terms in the derivative of that parentheses. Here I won't need a parentheses, but I could have it. Derivative of 3x is 3, the derivative of 9 is 0, so I just need a 3 here. Now I'm going to write g prime of x equals to 12 times 3x plus 9 cubed. 2 more and we'll move on to the section. So if I did h of x equals 2/3 times the square root of 5x plus 14. So it's an ugly square root, sorry about that. I have to write this with a fraction exponent. So this can be thought of as 2/3 times 5x plus 14 to the 1/2 power. Now I'm going to write h prime of x. I'm going to bring the exponent down and multiply it by the coefficient. So I'm going to go 1/2 times 2/3. I leave myself some room, and then I take the original parentheses and lower the exponent by 1. And where I left that room, I put a times sign, or I could put a parentheses, which is replaceable, it's interchangeable with times, and I write the derivative of 5x plus 14. The derivative of 5x is 5, the derivative of 14 is 0, so I'm going to put a 5. I'm going to kind of write it high, just so you know it's going to be multiplied by the 1 and the 2, not the 2 and the 3. Now I'll finish this up. I'm going to get h prime of x equals, and for these three I'm going to multiply those and get 10. Should have canceled the 2 and the 3, but I didn't. The 2 and the 3 I'll multiply and get 6. And then I'm going to have 5x plus 14 to the negative 1/2 power. I'm going to make that exponent positive by moving this down to the denominator. So I'm going to get h prime of x equals 10 over 6 times 5x plus 14 to the 1/2 power. I'm going to reduce the fraction, and I'm going to write this with a square root. So the best derivative using the shortcut to the chain rule is 5 over 3 times the square root of 5x plus 14, because 1/2 power can always be turned back into a square root. One more, and then we'll move on to the section. So how about y equals 2 times x cubed plus 3x squared minus 6x plus 4 to the 7th power. Again, it has a parentheses with an exponent, so the chain rule is the proper way to take the derivative. The shortcut to the chain rule, I'm going to take the exponent, multiply it by the coefficient, leave myself some room for the derivative of the inside of the parentheses. That's going to be a big derivative or a long derivative, so I left myself a lot of room. Lower the exponent by 1, and now I'm going to put a parentheses, and the derivative of the inside of the parentheses, the derivative of x cubed is 3x squared. The derivative of 3x squared is a 6x, and I get that plus sign still. The derivative of minus 6x is minus 6. Derivative of 4 is 0. I'm going to multiply the 7 and the 2 and get a 14. If I wanted to, I could factor out a 3 here, but I'm not gonna, because I'm not doing anything with the derivative but taking the derivative. And so generally I don't use the chain rule how it's written with the f of x and g of x, because it takes a little bit too long. But a lot of times when I introduce the shortcut to the chain rule, students always forget this part, taking the derivative of the insides of the parentheses. And if you forget that part, then it's wrong. So it's important to put that part in if you're going to use the shortcut to the chain rule. So we have a few derivative rules so far. We have power rule, product rule, quotient rule, chain rule, which I'm going to shortcut. And we're going to introduce 4 new rules in this section. I'm afraid this section is a bit long. But the first rule we're going to learn is for a derivative of e, I'll say to the g of x power. Now the rule is going to be if f of x equals e to the g of x power, and this notation is more cumbersome than it actually is in application. Taking the derivatives with a e of x is actually quite easy. The derivative is going to be f prime of x is going to be the derivative of the exponent times the original function. So when we have e's, we don't lower the exponent by 1 like we generally do for almost every other derivative. When we do e's and logarithms in this section, the rules are a lot different for taking the derivatives. So let me try to apply those rules. They're really easy to apply. So the first few problems should go kind of quickly. So 1 and 2 want me to apply, it's an e to some power, and that's what the rule means. So in this case, the g of x is 7x. The derivative of this, I'm going to write y prime equals, I write the original function down, but I give myself some room because in the formula you get the original function back. To the left of the original function you write the derivative of the exponent. The derivative of 7x is 7, and that's the whole derivative. The derivative of e to the 7x is 7 times e to the 7x. I guess I could have written those a little bit closer together. So e is my favorite derivative because it's just super quick. I'm technically using the chain rule when I'm doing the derivative of an e, but I don't want to get into that. That is way more complicated than it needs to be. So 4 and 3 should go equally quickly. I'm going to write g prime of x because I'm taking the derivative, and anytime I take a derivative with an e, the original function comes back as part of the derivative, and right to the left of the original function I write the derivative of the exponent. The derivative of the minus 1 is 0, the derivative of 9x is 9, so right to the left of the function I'm going to write 9. So the derivative of e to the 9x minus 1 power is 9 times e to the 9x minus 1. These couldn't be easier. They don't simplify at all, so they just are what they are. For question 6, I'm going to write f prime of t. I'm going to write an equal sign. I'm going to leave myself a little room, and I'm going to write the original function, e to the 7t squared minus 3t plus 1. And now, because the derivative is more than one number or more than one term, I'm going to write a parentheses. And inside the parentheses, I'm going to write the derivative of the exponent. The derivative of 7t squared is 14t. I'm going to bring down that minus sign. The derivative of 3t is 3. The derivative of 1 is 0. And that's it. So these are the best problems, I think, for any derivative other than like the beginning power rule. If you have an e function and there's a number in front of it that doesn't have an x, then you can just multiply the derivative of the exponent by that number. If this 8 was an 8x, and I'd have to use the product rule. But let me pretend that I didn't know a shortcut to this, and I thought of this, I'm thinking of this as 8 times e to the 2x plus 5, and anytime we have a multiplication, we can use the product rule. If one of the terms in the multiplication doesn't have a variable, we can skip the power rule, product rule should I say, but I'm going to use the product rule here just to show you. Remember the product rule, we take the derivative of the first parentheses times the second parentheses, and there aren't parentheses here, but I can introduce some parentheses if you want to see them. It's really, I probably should have said derivative of the first factor times the second factor times the derivative plus the derivative of the second factor times the first factor, because we're not going to always have parentheses, and the objects being multiplied in a multiplication problem are called factors. So the product rule would say g prime of x equals the derivative of 8. The derivative, so it's going to be the derivative of 8 times e to the 2x plus 5 plus the derivative of e to the 2x plus 5 times 8. The nice thing about this is you get a lovely 0, because the derivative of 8, because it doesn't have an x, is 0. So this piece is 0 times e to the 2x plus 5. And then plus, I'm going to write the derivative of e to the 2x plus 5. I write the e to the 2x plus 5 down. And right to the left of it, I write the derivative of its exponent. The derivative of 2x is 2. The derivative of 5 is 0. So I'm going to write a 2 to the left of it. And I can leave this 8 after the function, or I can drop it and move it before the 2. It's probably better to move it before the 2. This piece is equal to 0 because 0 times anything is 0. So I'm just going to multiply the 8 and the 2 and get a 16, and then e to the 2x plus 5. So the trick would be to know that if you have a number multiplied by an e function, if that number doesn't have a letter, you don't really need to use the product rule because one of the pieces is going to turn to 0. But if that 8 had an x along with it, then I would absolutely have to use the product rule. Ten is absolutely a product rule because there's 2 factors. I can throw parentheses in if you need. So I need to use the product rule. So I'm going to write y prime. I'm going to write dy dx just to keep that symbol fresh. So product rule says I need to take the derivative of 3x to the 4th, then multiply that by e to the x, and then a plus sign, and then I do the derivative of e to the x times 3x to the 4th. So the product rule says derivative of the first factor times the second factor unchanged plus the derivative of the second factor times the first factor unchanged. And that's what I'm using here to do this derivative. The derivative of 3x to the 4th, I go 4 times 3 is 12. I lower the exponent by 1 to x cubed, and then I keep this e to the x intact because it's not changing on the first step of the product rule. Bring down my plus sign. Now I'm going to do the derivative of e to the x. To do a derivative of an e, you write the e function down, and to the left of it you write the derivative of the exponent. Well, the derivative of x is just 1. So right to the left of it I'm going to write a 1. And then this 3x to the 4th I can write after the e or before the e. It's almost nicer to write it before the e. So I'm going to get 3x to the 4th times 1e to the x. And let me just do that, multiply that 3 times 1. I don't really need that times 1 there. So I get dy dx as 12x cubed e to the x plus 3x to the 4th e to the x. And most of the times when I'm doing e's in the product rule, there's going to be a common factor I can factor out. And here there's a lot of common factors. Between this 12 and this 3, I'm going to factor out a 3. Between this x cubed and this x to the 4th, I factor out the smaller exponent of x cubed. And between this e to the x and that e to the x, I'm going to factor out an e to the x. So my common factor is a 3, an x cubed, and an e to the x. So for the first term, I divide the 12 by this 3 that I factored out, and I'm left with a 4. I took all of the x cubed out, so there's nothing left from the x cubed, and I took all of the e to the x out. There's nothing left from the e to the x. So what's left before this plus sign is just the number 4. After the plus sign, I divide the 3 by 3 because I factored out a 3, and I get a 1. I'm not going to write that 1. I had 4 x's. I took 3 away. I'm left with an x to the first power. And I took the entire e to the x out, so there's no e to the x left. So all I'm left with is a 4 plus x. I probably would write that in a better order, but that's a completely good answer. But this is probably a better answer. 3x cubed e to the x times x plus 4 is the derivative for number 10. So hopefully you're pausing the video and doing your odd numbered problems. For 12, I'm going to use the product rule. So I'm going to go, first I'm going to do the derivative of 2y minus 3. I'm going to multiply that by e to the 5y. And then plus the derivative of e to the 5y times 2y minus 3. So, 2 derivatives to get done here. First derivative, the derivative of 2y minus 3 is just 2. And I'm going to leave that multiplied by e to the 5y. Bring my plus sign down. And then for the derivative of e to the 5y, the derivative of the exponent is 5. You multiply the derivative of the exponent by the e function. Now I look for common factors in all these e problems which have the product rule. There's going to be at least a common factor with an e that I'm going to factor out, and that's the case here. I'm going to factor out the e to the 5y. I'm going to get f prime of y equals e to the 5y times, I'm going to be left with that 2, this plus sign, and this 5 times 2y minus 3, because the e to the 5y goes away. And that's going to give me f prime of y equals e to the 5y times 2 plus 10y minus 15. I'm going to subtract the 2 minus 15 and get a minus 13. And the best answer for number 12 is f prime of y equals e to the 5y times 10y minus 13. Alright, 14 doesn't look near as nice, but I can deal with it. So for 14, I have these horrible parentheses with an exponent. So y prime is going to be the derivative of 7x plus 1 cubed times e to the 6x plus the derivative of e to the 6x times 7x plus 1 cubed. This derivative, the derivative of 7x plus 1 cubed, I'm going to use the shortcut to the chain rule, meaning I'm going to bring the 3 out in front of the parentheses. I'm going to leave myself a little bit of room. I'm going to lower the exponent from 3 to 2, and right next to where I had the room, I'm going to write the derivative of the inside of the parentheses. The derivative of 1 is 0. The derivative of 7x is 7. So that's the shortcut chain rule that I used. And I'm going to bring down this e to the 6x. Eventually, I'm going to multiply this 3 and 7, I think. For the next piece, the derivative of e to the 6x, I take the derivative of the exponent. The derivative of 6x is 6. I multiply that by the e to the 6x, and then I have the 7x plus 1 cubed. I could, on the next line, multiply this 3 and 7, but I'm going to have a big old common factor, and that 3 is going to be part of my common factor, so I'm not going to multiply that out. So now I'm going to look for common factors. Between that 3 and that 6, there's a common factor of a 3. Between this 7x plus 1 squared and that 7x plus 1 cubed, there's a common factor of 7x plus 1 squared. You take the smaller of the exponents. And between this e to the 6x and that e to the 6x, I'm going to factor out an e to the 6x. There's my common factor, and I'm going to leave a parentheses. From this piece, I took the 3 out entirely, so it's gone. The 7 I didn't do anything with. It's going to be first. I took the entire 7x plus 1 squared out, so it's gone. I took the entire e to the 6x. It's gone. The only thing that's left to the left of the plus sign is that 7. To the right of the plus sign, this 6, because I factored out a 3, I need to divide by 3. 6 divided by 3 is 2. I took out the e to the 6x, so it's gone. And the 7x plus 1, I took out 2 of them, so there's 1 of them left. Now I'm just going to clean up this a little bit. I'm going to get y prime equals to 3 times 7x plus 1 squared times e to the 6x times 7 plus 14x plus 2. I'm just going to add the 7 and 2. I'm going to get y prime equals 3 times 7x plus 1 squared times, I didn't need a parenthesis for that e to the 6x, I just accidentally put it there. That's the derivative. The only thing I might do differently is the e to the 6x probably would be written before the parentheses, so maybe the best way to write this is 3 times e to the 6x times 7x plus 1 squared times 14x plus 9. So that's messy, but I don't know, we're going to have messier things. I think even in this section we're going to have messier things. (16) is also a messy problem. It's just like 14, but it looks a little bit longer. So I'm going to leave myself some room here. So y prime is going to be first the derivative of x squared minus 3x plus 1 cubed times e to the 2x plus the derivative of e to the 2x times x squared minus 3x plus 1 cubed. When I do this derivative, I'm going to use the shortcut to the chain rule. So my next step, y prime, I'm going to bring this 3 out in front of the parentheses. I'm going to leave myself some room, and I'm going to take this and lower the exponent by 1. To finish up the shortcut of the chain rule, I have to multiply by the derivative of the inside of the parentheses. Because it's more than one term, I'm going to put a parentheses here. The derivative of x squared is 2x. The derivative of minus 3x is minus 3. So that whole big thing is just a derivative of that. I still have to tack on this times e to the 2x. I probably didn't need the times sign, but it's okay to have the times sign. I'm going to bring down this plus sign, and then I'm going to do the derivative of e to the 2x. That just multiply the derivative of the exponent by the e function. The derivative of 2x is 2. So the derivative of e to the 2x is 2e to the 2x. I still need this part, the x squared minus 3x plus 1 cubed. Now I look for common factors. I'm going to get y prime equals, and there's a big parentheses with a squared and that big parentheses with a cubed. I take the smaller exponent, so I'm going to take the squared one. So I'm going to have an x squared minus 3x plus 1 squared as part of my common factor. And I have an e to the 2x and an e to the 2x. That's going to be the rest of my common factor. So the common factor is going to be the x squared minus 3x plus 1 squared times e to the 2x. I'm left with all of this, 3 times 2x minus 3 from the first factor. Bring down my plus sign. From here, I still have left with that 2, but I took out 2 of those, so I'm only left with 1 of those. So that's what's left. Now I'm going to clean up that mess there. I'm going to get y prime equals, I'm going to write the e first, just because I usually write it first. So the common factor I wrote in a different order. And I'm going to clear the parentheses. 3 times 2x is 6x. 3 times minus 3 is minus 9. 2 times x squared is 2x squared. 2 times minus 3x is minus 6x. And 2 times 1 is 2. Now I'm just going to clean up these. I'm going to get that 2x squared first. 6x minus 6x cancels. Minus 9 plus 2 is minus 7. So that's the whole simplified derivative. E to the 2x times x squared minus 3x plus 1 squared times 2x squared minus 7. All right. So product rule again. So first I'm going to do g prime of x equals the derivative of x times e to the negative 3x plus the derivative of e to the negative 3x times x. The derivative of x is just 1. I'm not even going to write, I'll write that 1. What the heck? Can't hurt. That's the first piece. The derivative of e to the negative 3x, I'll take the derivative of the exponent, which is negative 3, and I multiply that by the original function, e to the negative 3x, and I still have this times x. Done with the derivative, now I look for common factors, and the only common factor is e to the negative 3x, because there's one on either side of that plus sign. So I'm going to factor out that e to the negative 3x. And I'm going to get e to the negative 3x. To the left of the plus sign, I'm left with a 1. To the right of the plus sign, I'm left with a minus 3x. And then rather than writing plus a minus 3x, I'm just going to write a minus 3x. That's a perfectly good answer. Because the original problem had a negative exponent, I don't feel bad about leaving the negative exponent in the answer. but if you wanted to, you can certainly make that negative exponent positive by dragging the e to the negative 3x into the denominator of a fraction that you create. And that would be absolutely probably a perfect way. You could write the numerator as negative 3x plus 1 if you'd want to. Generally, we don't write negative exponents in our answers, but if the original problem has a negative exponent, then maybe it's not so bad to keep that negative exponent in our answer. '20 is just a pure chain rule because there's only one parenthesis with an exponent. When you have one parenthesis with an exponent, you usually use the chain rule. So I'm going to write y prime equals, and I'm going to do the shortcut to the chain rule. So I'm going to bring the exponent down, which is negative 1, leave myself some room, and I'm going to write e to the 4x plus x squared, lower the exponent by 1, negative 1 minus 1 is negative 2, and then I'm going to put a parenthesis because there's going to be two terms. The derivative of e to the 4x is 4e to the 4x. The derivative of x squared is 2x. That's the derivative. I don't need the 1 with the negative, so I can say it's y prime equals negative 4e to the 4x plus 2x times e to the 4x plus x squared to the negative 2. There's no common factors, nothing combines. I can write this problem with a positive exponent if I care to, but you don't have to. If the original problem is stated with a negative exponent, then we don't feel so bad about keeping the negative exponents in our answers. But anytime you have a problem, if you want to make a negative exponent positive, you can introduce a fraction if there isn't already a fraction and tuck that term with a negative exponent down to the denominator. Ay, 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 a lot of problems. '22 is a quotient rule because it's a division problem. So I'm going to use denominator times derivative of the numerator minus numerator times the derivative of the denominator all over the denominator squared. So g prime of t is going to equal the denominator, e of t, times the derivative of the numerator, which is t cubed, minus the numerator, t cubed, times the derivative of the denominator all over the denominator squared. All over the denominator squared. So, not messy because it might have some algebra tricks that you don't remember or that you never really were exposed to. The derivative of t cubed is 3t squared, and I can write that before or after the t. I kind of like it before the t. So I can write e to the t times 3t squared, or I can write but I wrote 3t squared times e to the t. And then minus, I'm going to bring down the t cubed, and then the derivative of e to the t, I take the derivative of its exponent, which is 1, times the e function. I'm going to leave, well, heck, I'm going to write this as e to the t times e to the t. It's going to make it easier to see the canceling that's going to occur on this problem. So for e to the t squared, I wrote it without its exponent. Now in the numerator, I'm going to pull out my common factors. Between a t squared and a t cubed, there's a common factor of t squared. They both have an e to the t, so I'm going to factor out an e to the t. And then I have a parenthesis. From here I'm left with a 3, left with a minus sign. There were 3 t's. I factored out 2 of them, so I'm left with 1 of them. I don't really need to write this one, but I could write it and precede the t with it. I factored out that e to the t entirely. So what's left in the numerator is a 3, and from there a minus t. And now in my denominator, I have e to the t times e to the t. One of the e to the t's will cancel. And I'm going to get, for an answer, g prime of t equals t squared times 3 minus t over e to the t. And that can't reduce at all. That's the nicest form of the answer for 22. So you should be able to mimic that when you do 21. It should be almost the same problem. Hopefully you're finding that a lot of our problems are kind of a lot alike. Just do it. There's some trickery that I might not get into in terms of the factoring of common factors here, because I don't know how important it is. If it becomes important, I'll talk about it later. So it's quotient rule because it's divide. So y prime is going to be the denominator, x, times the derivative of the numerator. So I need the derivative of e to the x minus e to the negative x, minus the numerator times the derivative of the denominator. The numerator is e to the x minus e to the negative x, and then I have to multiply by the derivative of x, and then all over the denominator squared. So that's using exactly the rule. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And the derivative of e to the x is a mess. So y prime is going to, so the derivative of this parentheses is going to be ugly. I'm going to leave myself some room for it. Derivative of e to the x is derivative of the exponent, which is 1, which I'm not going to write, times the e to the x function. So when I'm doing this derivative, I do the derivative of each piece. The derivative of e to the x is 1 e to the x. And then this one right here, there's a minus in front of it already. When I do its derivative, the derivative of negative x is negative 1, so I get negative 1 times e to the negative x. And that double negative I'm going to put a positive for. I'm going to write positive e to the negative x. And then minus sign. I have to take the derivative of x, which is just 1. That's going to be e to the x minus e to the negative x all over x squared. You can't cancel that x with that x squared. I don't even know if I should clear the parentheses, but I'm going to. So I'm going to get y prime equals x times e to the x plus x times e to the negative x minus e to the x and then plus e to the negative x all over x squared. You can't combine any of these terms. Every term has an e to the x. You can technically factor out an e to the negative x, but right now I don't want to get into that. Let's just stop this here. The derivative was complicated enough to not introduce factoring out with negative exponents, which we haven't done yet. So I'm going to say that's the derivative, although it could be simplified. If you take a stab at simplifying it and want to show me, then I'd love to see it, but I don't want to go any further. But because each term in the numerator does have an e to the x, or some power of e, you can factor out an e. It's actually e to the negative x that could be factored out. So I'm going to call that the end of the part 1 because we get a new rule. And I don't know if I could do that new rule in the amount of time that I have left. I don't think I do. So let me pause the video.